When people ask whether artificial intelligence is biased, the question often sounds simple. But the word bias carries assumptions. It suggests intention, preference, even prejudice. Machines, of course, do not possess beliefs. They do not hold opinions. They do not form moral judgments. And yet, patterns appear. Certain answers surface more often than others. Some outcomes feel uneven. Some results raise uncomfortable questions. So the real question is not whether AI has beliefs. The question is something quieter. How do statistical systems inherit the patterns of the world that produced them? And what happens when those patterns become automated? For most of computing history, machines did exactly what they were told. Software followed explicit instructions. A developer wrote rules. The computer executed them. If a program made a mistake, the cause was usually easy to trace. A line of code, a faulty condition, a logic error. Bias, in that era, typically entered through design decisions. A programmer might define a threshold incorrectly, or choose categories that excluded certain cases. But the system itself remained deterministic, predictable, transparent. Modern artificial intelligence works differently. Instead of being told how to make decisions, many AI systems learn patterns from data. Large language models, recommendation engines, and image recognition systems are trained on enormous collections of human-generated material: books, articles, conversations, images. From this data, the system identifies statistical relationships, which words tend to follow others, which visual patterns correspond to certain objects, which behaviors correlate with particular outcomes. The machine does not learn meaning in the human sense, it learns probability. And probability reflects history. This is where bias enters the conversation, not as a moral quality, but as a mathematical inheritance. If the training data reflects uneven patterns in society, the model will reflect them too. Not intentionally, but inevitably. Consider a simple example. Imagine training an AI model to generate images when given a job title. The prompt might be straightforward. Generate an image of a CEO. The system searches its learned patterns. If the training data contained far more images of male CEOs than female CEOs, the generated images will likely reflect that imbalance. The model is not making a judgment. It is repeating a statistical pattern. In other words, it mirrors the distribution it observed. A similar effect appears in language systems. When a model completes a sentence, it draws from probabilities learned during training. Suppose the prompt reads, "The nurse walked into the room and." If historical text more frequently associates certain genders with that role, the system may reflect that association in its continuation. Again, the system is not expressing belief. It is reflecting frequency. This distinction is important. Bias in AI is often described as if machines were adopting human prejudice, but the mechanism is different. AI systems compress large datasets into mathematical structures. Within those structures live correlations. Some correlations are useful. Some are misleading. Some reveal patterns society would prefer not to repeat. Well, for a long time, this dynamic remained mostly academic. Early machine learning systems operated within limited domains. Spam filters, search rankings, product recommendations. The effects were real, but rarely visible to the public. That changed when AI systems began generating language and images directly for millions of users. Suddenly, the patterns inside training data became visible, not as abstract probabilities, as concrete outputs. A generated image, a written answer, a recommendation. The system's internal assumptions became observable. This visibility created a new category of discussion. Not just whether AI works, but how it represents the world. Governments began examining algorithmic decision systems. Researchers studied fairness metrics. Technology companies introduced evaluation frameworks designed to detect problematic outputs. The conversation expanded beyond technical performance. It entered the territory of social consequences. But the public discussion often simplifies the problem. One common narrative suggests that bias appears because developers intentionally shape AI systems to promote certain outcomes. Sometimes this happens, but most bias emerges from something more ordinary. Historical data. The past leaves traces, and machine learning systems learn from those traces. If the past contains imbalance, the model reflects imbalance. Another misconception is that removing bias is simply a matter of cleaning the dataset. In practice, the situation is more complex. Large training datasets contain billions of examples. Many patterns overlap. Correcting one imbalance can introduce another. For instance, if developers deliberately rebalance images to ensure equal representation of certain roles, the system may become less accurate at predicting real-world distributions. This introduces a philosophical question: should AI reflect reality as it is, or represent an adjusted version of reality? There is no purely technical answer. The choice involves values. Because of this, modern AI development increasingly involves layers of adjustment after training. Researchers evaluate outputs, test edge cases, introduce moderation filters, fine-tune models using curated examples. These processes attempt to guide system behavior toward outcomes considered responsible or useful. But they also reveal something important. Bias in AI is not a single switch. It is a spectrum of statistical tendencies. Managing those tendencies requires ongoing calibration. There is another dimension that receives less attention. Bias can appear not only in the data, but in the questions people ask. Consider a hiring algorithm trained to predict successful candidates. If past hiring decisions favored certain universities or backgrounds, the training data reflects those choices. The model then learns patterns that resemble historical hiring preferences. But the algorithm did not invent the criteria, it inherited them. In that sense, AI systems often expose institutional habits that were previously invisible. Automation reveals structure. Recommendation systems illustrate this clearly. Platforms that suggest videos, products, or articles are constantly optimizing for engagement. If users historically click more often on certain kinds of content, the algorithm learns to prioritize those patterns. Over time, this can reinforce existing preferences. Popular content becomes more visible. Niche content becomes harder to discover. The system is not choosing sides. It is amplifying behavioral signals. This feedback loop represents one of the most subtle second-order effects of AI. Automation can magnify patterns that were previously diluted. Human decisions contain variation. People occasionally act inconsistently. Algorithms, by contrast, repeat patterns with remarkable consistency. What was once a tendency becomes a mechanism. At the same time, AI can also reveal biases that humans overlook. When a machine consistently produces uneven outcomes, the pattern becomes measurable. Researchers can analyze error rates across demographic groups. They can examine how predictions differ under varying conditions. In some cases, AI systems have highlighted disparities that previously went unexamined. In this sense, algorithmic bias can function as a diagnostic tool. It exposes hidden asymmetries within data and institutions. Understanding this dynamic requires moving beyond a simple narrative of good or bad technology. AI systems are mirrors of the data environments that shaped them. Sometimes those mirrors are uncomfortable, but they are also informative. They show us patterns we might prefer not to see. There is another quiet shift happening as well. The scale of modern AI training datasets has increased dramatically. Earlier machine learning systems relied on relatively curated data. Today's models learn from vast quantities of internet-scale information. This diversity can reduce certain forms of bias, but it also introduces noise, contradictions, cultural differences, conflicting perspectives. The system must compress all of this into a single statistical model, which means the outputs inevitably represent averages, and averages rarely capture nuance. As AI becomes embedded in more decision processes from customer service to healthcare triage, the question of bias becomes less abstract. Organizations must evaluate not only whether a model performs well, but how its errors are distributed. A system that achieves high overall accuracy may still perform unevenly across different populations. Addressing this requires careful measurement, not just intuition. At this point, it is worth stepping back. The conversation about bias sometimes implies that AI introduces a new problem. In reality, uneven outcomes have existed long before algorithms. Hiring decisions, medical diagnosis. Human judgment has always been imperfect. What changes with AI is scale. Algorithms can apply patterns millions of times per day, which means their effects accumulate quickly. But the underlying patterns often originate elsewhere. This leads to a useful way of reframing the issue. Instead of asking whether AI is biased, a more productive question might be, what patterns does this system reproduce? And where did those patterns come from? When framed this way, the discussion shifts from blame to understanding. Bias becomes a property of data ecosystems, not simply a flaw in technology. Over time, the field of machine learning has begun developing tools to address these concerns. Fairness metrics measure how predictions vary across groups. Bias audits evaluate models before deployment. Researchers experiment with techniques that reduce harmful correlations during training. None of these methods eliminate the problem entirely, but they represent an evolving toolkit, one that treats bias as a measurable engineering challenge. For users, the practical takeaway is relatively simple. AI outputs should be interpreted as probabilistic suggestions, not authoritative truths. These systems are powerful pattern recognizers. But pattern recognition is not the same as judgment. Human oversight remains essential, especially in contexts where decisions carry real consequences. In the broader arc of technology history, the debate about AI bias reflects something deeper. We are transitioning from rule-based machines to statistical infrastructures. Machines that once executed commands now interpret patterns. That shift introduces ambiguity, but it also expands capability. AI can process signals far beyond human scale, which means it will inevitably encounter the complexities embedded in human data. The challenge ahead is not to eliminate every bias. That may be impossible. The challenge is to understand which patterns are acceptable, which require correction, and which reveal underlying structures worth examining. In other words, the conversation about AI bias is ultimately a conversation about society itself. Algorithms inherit our histories, they compress them, and occasionally, they make those histories visible. So when we ask whether AI is biased, the answer is neither simple nor alarming. AI reflects patterns. Sometimes those patterns are useful. Sometimes they are uncomfortable. Often they are both. The task is not to fear the mirror. It is to understand what the mirror shows. This is Neural Pulse Lab, examining the quiet mechanics of intelligent systems and the subtle ways they reshape how we understand the world.